Hi, everyone. We are back, and we are going to go through a very important section and lecture, which is poles and zeros of our transfer functions. Poles and zeros are incredibly important. They really are the keys to system stability, response essentially of our function and our system. It's really incredibly important. We have to know how to calculate poles and zeros. We need to know how we can leverage them to, again, the whole idea of this class is controlling essentially our system to control essentially those values. So let's say we have this transfer function. The zeros are the roots of the numerators. Basically, what's going to make this top part 0, or basically make this 0. So zeros are the roots of the numerator. Poles are the roots of the denominator. The poles are actually the most important. Zeros are important. You can kind of tune that to change some response, but the poles are critical. Poles are going to determine our stability, which makes sense because our transfer function goes to infinity and et cetera, et cetera. But anyways, at least mathematically. So poles will determine stability, frequency, damping behavior, lots. Zeros will affect essentially response shape and all these other things. So let's look at an example. So we have a plant function, a delta function input. You're going to, when you hear this word, or when u of t, a delta function is just this, or, and sometimes I might say like a step function, and, I kind of use this interchangeably. I'm going to try not to, but a delta function, if you look at our Laplace transform, so if we say, new Mathematica download, that's going to be the question. And let's go over here. Let's say I do, so let's say I do a Laplace transform of delta of t, delta function. Dirac delta of t, comma s. 1. So if I give you a Dirac delta or delta function, the Laplace transform, so my u of s in that scenario would just be equal to 1. So if this is our plant function, if we have our input, and again, our command, I'm referring to our command input. So, I'll try to be very clear with the language, but just, we're gonna kind of get more familiar with it, and you're gonna kind of understand the shorthand soon. So this is our plant function. This is our response. So we're going to have poles in this scenario where s equals minus infinity. If we take the inverse of that Laplace transform, now you have basically this response of our function, and you see it's this exponential decay. So we can actually see that here. The cool part about Mathematica, and especially when you're dealing with poles and zeros, is if I have, so for example, and so if this is my plant function, I can look and create a transfer function model, and then I can find what's the transfer function zeros. Nothing here because we can't make it 0. What are the poles? And you can get those automatically. Now, obviously, in this one, it's pretty trivial. I think we could all kind of see those immediately. But as the functions get more complex, you can leverage essentially this and essentially find some. Now, if I wanted to see the time response, inverse Laplace transform, and I can have that, and then you can kind of see, I actually did an animated video, but we can actually do, instead of this, I can do, for example, manipulate, and we can see how does the system respond as we increase. I'm just going to increase this here. So we're varying in this instance a, which is basically sigma. Actually, I'm going to just say it just for ease, sigma 0 or whatever. And then this goes to sigma 0. There we go. So here I'm just going to kind of, you see, as I increase the value of sigma, you see I'm getting a kind of faster exponential decay. So I'm essentially changing that system response depending on what that value of sigma is. So you can kind of start to see, again, the response, the stability, and especially like the natural frequency, or, this is effectively our damping, right? So the damping behavior, or actually really this is the exponential decay behavior, you have a faster, essentially a decay, depending on that value. So you can start to see that depending on your function, and this could be, right, this could be some type of physical parameter in your system. So remember, the plant function is a function, when we're looking at, and actually this is perfect relationship here. Let's go back to our classical example of our spring mass damper system here. Let's say this f of t is really just our u of t, which is our command input. Let's ascend a delta function. And now you can see that you have s, just quadratic formula, but you see you can change positions of these poles depending on these physical constants. So that's kind of the same idea here. Depending on your system, and if you can tune some of the parameters, you can change the response and the control of your system. And you can see if we are working with our good old friend, our spring mass damper system, you can see here's our u of s. This is our x of s. If we did the Laplace transform, we're setting all the initial conditions equal to 0. We can just rewrite it as this. Again, we don't have any zeros, but we do have poles, and we have 2 poles. Because, again, second order system, we can solve for that. It's our good old friend, the quadratic formula. And now, depending on some of these physical parameters, you can either get a critically damped system, an overdamped system, or an underdamped system. And you can essentially see that response. So if we can see an overdamped response if we set, I can set, for example, 1, m equal 1, c equals c set to 3, and get those. So again, zeros, nope. Transfer function poles here, excellent. And then now I can do example 1 like this, and I can see what the response is. And you see kind of this input, and then now this overdamped system. Fantastic. So this is an overdamped response, no oscillations, it's overdamped. Fantastic. So that's the first example, overdamped system. We've got it. What if we are, let's look at some oscillations if we're underdamped. And let's say we have some complex poles. So you'll notice, again, if I'm overdamped, I'm going to have 2 distinct real poles. If I'm underdamped, I'm going to have a pair of complex conjugate poles. So let's go ahead and look at an underdamped system. Oops, I'm just going to set this to this. I'm going to set here. Now we have a pair of complex poles. If we take the inverse Laplace transform, you're going to see, no oscillations, overdamped. We're going to see, we do see oscillations. So excuse. Did I read it run this one? This one, yes. So, yes, oscillations underdamped. So you see essentially the oscillations that are occurring in that system. So, and that's for, let's double check, m equals 1, c equals 1, k equals 2, and we can see that right here. Fantastic. Now, we see that. One thing that you can see in the output of the function is that imaginary component is going to control essentially the oscillation frequency, and the real response basically appears in the exponential term as well. So, what about a system where c is equal to 0? So now you can see our plant changes, and now we're going to get a response that is purely oscillatory. So it's just a sinusoidal function. So there is no decay component. And we can see that because in the imaginary component, which is our oscillatory behavior, the real part is our decay. So if there's no real component to that pole, we're just going to get a sine wave. Cool, isn't it? Fantastic. Again, I always think these are kind of, fun edge cases. So you can kind of see, again, we're controlling the oscillations from this term. So next time we're going to look at another example, and then we're going to kind of map out based on pole location in what's called the S domain. We're going to kind of see how we should expect the system to respond to. So we'll see you in the next video. Thanks. Bye.